Okay, so we're going to look at just a graphical way to deal with some aspects of motion. Okay, so I want to introduce you to the idea of position time graphs. So let's take an example. Let's say I'm going to do my example. I'm walking along the front of the room, and I want to see if we can turn this into a graphical story. Okay, so here's my story. It's a real exciting one. I'm going to start from rest, and let's say I'm just going to be walking along at constant speed. We're going to click the stopwatch when I pass 0. Okay, so click the stopwatch, stop the stopwatch. Okay, and that's the story. Pretty boring, right? I walked at constant speed from 0 out to 5. Let's say. If I wanted to graph that on a position time graph, what would that look like? Now think about that. We've got position time. So time is going to go on this axis, right? Position is going to go on this axis. Okay. And what? Okay, good. So it's going to be, we're going to get a graph that's going to look something like this, isn't it? It's going to start here, and then I'm going to walk a total of, let's say I walked a meter per second for 5 seconds. So. Wouldn't it just look like that? Everybody agree? Okay, makes sense? So a point on this graph represents my position at that time, right? So you could read this graph if I wanted to know, for example, what's my position at 3 seconds, what would you do? Go over to 3, go up to 3, and it's right there, right? Everybody see that?
Do you have any recyclables?
Oh, I probably do. Oh, I don't today. Thank you.
Cool, we'll be back later on in the week.
Thanks. Does that make sense? Okay. What does the slope of this line represent?
Meters per second.
Ah, okay. Velocity, isn't it? Right? It's velocity, right? Think about that. Now think about, this is where I think this is extremely helpful mathematically, because it gives you, once you start studying physics, like my background's in physics. I mean, I like math, and I teach advanced math, and I've taken a lot of advanced math. But I like the physics part better. To me, the math always got a lot easier when I had something to kind of, a context to put it into, right? And physics is the best at that. Other things work, but physics is the best because physics is essentially math, right? It's just mathematical models as they pertain to the real world. So this is helpful. This is going to take a lot of the math you've done in the past. It's been kind of abstract, and you probably can do the problems really well. Obviously you're all good math students, but I think it takes it one step further. It kind of gives it more meaning, and so when you start to tie things together like that, you understand them better. Okay. So yeah, think about this in terms of what you know about lines, right? The slope of a line is just rise over run, isn't it? Right? So if we were to go from, for example, let's say we're going to go from this point right here up to this point right here, and we're going to calculate a slope triangle. Well, what is that? We're going to rise by, I didn't draw this very well, it's supposed to be more up there, I guess. We're rising by what? 2 meters, because presumably, I guess we're measuring distance in meters, right? We're measuring time in seconds. So 2 meters, and we're running how far? 2 seconds. Okay, good. And so then if we take rise over run, my slope is equal to 2 meters over 2 seconds, which is 1 meter per second, isn't it? Right? So we can see the units are consistent with the speed or velocity, and actually so is, if you think about it, so is the definition, because we define average velocity as change in position, right? What we call displacement over change in time. Well, isn't that just rise over run, right? The rise is literally the change in position. We normally would have said, back in math class, we would have said change in y over change in x, right? Delta just means change in. Okay? But we don't have y's, we have d's. We don't have x's, we have t's. And so you can see right from this graph But that has to be the case, doesn't it? Right? The slope is equal to the average velocity, okay? We could even go maybe one step further than that. What if I took, same kind of an idea here, but I guess before I go any further, I do this sometimes, I get excited and I want to go move on and talk about something new. Any questions on that? Does that make sense? Okay, it'll make more sense here in a second. Let's look at this. What if we do the same kind of a thing? Only this is the graph, we're gonna go the other way. This is the graph I'm gonna draw, and you tell me what story this represents. What if we went Thank you. Tell me, what about that story? Same deal, we're measuring, this is a graph of position versus time, position in meters, time in seconds, let's say. What story is that? Okay, I'm starting already at 2 meters, good. And over a course of 4 seconds, I'm moving 2 more meters. Okay, so then you can already see that my slope is, if I were to draw a slope triangle, my rise is 2 meters, right? My change in position is 2 meters. My run is 4 seconds. So my slope is 1/2, right? Everybody agree? 2/4? What's my start value or my y-intercept? 2. Okay, so what's the equation of this line then? Okay, so mathematically, it would have looked like y equals 1/2 x plus 2, but we don't have y's and x's. This isn't just a mathematical abstraction. These are real quantities, right? And we get position equals 1/2, okay, 1/2 meter per second times t plus 2 meters, right? Well, that's just a velocity, right? And that's just my initial position, isn't it? That looks familiar, I bet, doesn't it? Remember the equation, position equals initial position plus average velocity times time? Did we get that one last time? I think I gave that to you, right? Right, we said that, and we kind of worked backwards to get there. We worked, well, it's been a little bit ago. We worked backwards. We started with the definition of average velocity, right? We said average velocity equals change in position over change in time, and we just solved for change in position, right? We said, oh yeah, okay, well then, if I multiply each side by delta t, don't I just get displacement, change in position equals v bar, delta t is just t, right? Starts at 0 always anyway. And then what is delta d? Well, delta d is really just d minus d naught. And then if I just add that to the other side, look what I get, right? That's how we kind of looked at it last time. And we came up with this fancy equation that we're able to use, this kinematic equation. Okay, what I want you to see here, though, is that this is just consistent with the graph, right? Okay. Make sense? All right, so let's try something a little trickier with this. What do you think it's going to look like? Here's a new story. This time I'm going to start at rest. I'm going to start the stopwatch, and I'm going to pick up speed as I go. I'm going to uniformly accelerate. So I'm picking up speed at a uniform rate, constant rate. What's that going to look like? Okay, it is. It's going to look like this, isn't it? It's going to look like, yeah. Okay, does that make sense? Now that picture seems really simple, but there's a lot of information there. A lot of information. What's happening to the slope of that line? Okay, it's increasing, isn't it? Right? Now, this is where we finally get to start talking about instantaneous velocity, right? Would you agree that that if I were somehow, if I had like I was tracking myself with GPS and I was getting a constant readout of my speed, like a speedometer, right? I'd start at 0, and as I moved along, my speedometer would be getting bigger. I'd be getting bigger readings, and we can consider that a velocity because it's moving in the positive direction, so my velocity would be increasing. Yes.
Is this the tangent?
Yes.
Is.
Yeah. So if you were in calculus today, you saw this. You saw this from a little different perspective. But so, how are we going to somehow try to ascertain what my instantaneous velocity is from this graph? Because we're used to calculating average velocities, right? An average velocity, like if I wanted to calculate my average velocity from, say, here out to there, well, we can do that, right? I just create a line segment, calculate the slope of that line segment, right? So that represents average velocity of, well, what do we do? This was position and that's time, and so if we make a slope triangle out of it, it's just change in position over change in time is the slope of that line, right? It's an average velocity. Okay, that's a different shape than that is, though. Right? Would you agree? Would you agree that when I start this story, am I traveling at a speed or at a velocity that's greater than or less than my average velocity for the whole trip? Less than. Okay. When I finish my trip, is my instantaneous velocity greater than or less than my average velocity? Greater than, right? Everybody agree? Okay. How could I see that from the graph? Okay, because of the slope, and that's a different concept, because of the slope of the curve. We usually talk about the slope of a line, right? Because a slope is defined in terms of a line, isn't it? What do you mean by the slope of the curve? Let's pick this time right here, for example. How do you represent the slope of the curve at that point? What do you think? Yeah, see, that's the weird part about it. You have to pick another point, right? And somehow get an average. We started talking last week a little bit, though. Remember we had the example of like if we're going to go to Hermiston, it's more accurate for us to take a short interval right around Rue Elevator. If we want to know how fast we're going by Rue Elevator, we wouldn't take the whole trip. We might take just a mile segment, or even better than that, like 100 meters. Or if we want to be really accurate, even just like 1 meter, right? But if we wanted to take that to its logical extreme, we want to make that segment as short as possible, right? Well, yeah, so what happens if I take these 2 points and I start to shorten up this segment by pulling the points closer together? Eventually it starts to look not like a secant line, which is a line that connects 2 points on a curve. It starts to look like a line that only hits the curve in one place. What do we call that kind of a line?
A tangent.
That's a tangent line, right? Do you remember, raise your hand if you've heard about tangent line. I know you've talked about it, but it may have been a long time ago. Raise your hand if you've heard this, if you've heard the term tangent line. Okay. Okay, but maybe some of you have never even heard that before. It's not a big deal. We're not going to get into the math. By the way, this is, in calculus, this is what we're doing. In calculus, we're talking about how to, using calculus, how can we represent the slope of that tangent line? Or how could we find the equation of the tangent line? We're not going to do that. I mean, this isn't calculus. This is, we're not going to be that math heavy. But really all it is, would everybody agree that this line segment right here, and if I extend it out forever, by extension, that line, maybe I'll put arrows on the end. The slope of that red line really represents the slope of the blue curve at that point right there. Would you agree? Okay. Down here a little further this way, maybe that's the red line that represents the slope of the blue curve. Those are called tangent lines. Okay. So this is I'm going to make some definitions here. So that's what we call a point of tangency, and the red lines are called tangent lines. you could already probably define what a tangent line is. What does it mean to be a tangent line to a curve? Okay, so it only touches the curve in one important place. It might be, it's possible that what if my graph did this later? What if it did something like it looped back around? Well, then this tangent line might intersect at someplace else incidentally, but that's just an accident, right? That's not the one we're talking about. What we say in math is, locally speaking, so for the x values around this particular x value, it only intersects once, right? And that's not enough though, because here's a line that intersects this curve at only one spot, but it's clearly not tangent. What else has to be true? Maybe the most important part. So it intersects the curve at only one point, but there's something that's happening at that one point that's really important. What is that? What's going on there at that point? You can see there's something important, right? You told me it looked to you like that red line was a good representation of the slope of the blue curve. Why? Okay, it has the same slope at that point. Weird concept. How can a curve have slope? I mean, it just seems like that's completely crazy, right? That a curve could have slope. Well, let me ask you this: is the Earth spherical? We would agree it's probably spherical, right? You've seen pictures of the moon, or the Earth from the moon, and you can block the Earth out with your thumb. But if you're standing in a wheat field outside of Pendleton, you might have a hard time convincing somebody, if they didn't know any better, that the Earth was not just flat. In fact, that was a real dilemma. If you go back not that many centuries ago, that was a real problem. And people did think the Earth was flat. I mean, you'd be stupid not to. It looks pretty flat, right? How come? Why does it look so flat to us? Okay, because our frame of reference is so small compared to the entire curve, right? In other words, we're zoomed in, right? We're right on the surface of this thing, and we're only 2 meters tall, and the Earth is something like 6 million meters in radius. And so from our perspective, zoomed in this far, it looks pretty flat. If I were to take this curve, and I were to, let's say we were looking at this on a computer or in a microscope or something, if I were to keep zooming in and zooming in and zooming in, what's going to happen to the curvature? Oh, it's going to disappear, isn't it? As we get closer and closer and closer, the curve is going to flatten out, right? If we did that infinitely, wouldn't you agree that this curve is going to become absolutely linear at that spot? Okay, so at that point, then, wouldn't the red tangent line and the blue curve be one and the same? That's a tangent line, right? So a tangent line really just has two characteristics. It has to hit the curve in one place, and it has to have the same slope as the curve at that place. Meaning, if we were to infinitely zoom in, they'd look the same, right? Does that make sense? Okay, complicated description for really something that's pretty easy to see conceptually. Does it make sense then that the slope of this tangent line would represent the instantaneous velocity? Right? Everybody see that? That's all you need to know, honestly. This is not a calculus-based class, and so that's all I really want you to see is just that the velocity is changing here, right? Okay, so I messed this up. Let me redraw this a little bit. So we're going to go back to our picture. Then try to redraw this. So there's position, there's time. Here's the story that we told, right? So the instantaneous velocity is increasing because the tangent to the curve is getting steeper. Everybody see that? There is, incidentally, there is one place on here, there's exactly one time during my little interesting story here where my instantaneous velocity was the same as my average velocity. Can anybody spot that on this curve? Where that would be? So once again, the average velocity is the slope of the secant line connecting the endpoints, right? Yeah, it looks like I drew that. Well, that's pretty good. But you get the idea. Yeah, it's pretty close to the middle, isn't it? All we got to do, in fact, I can be really tricky with this. I like playing with my toys. Let's try that. Something like that. there's the line that represents the average velocity, right? Well, isn't right about there, that must be the point right there where the instantaneous velocity is equal to the average velocity, because they're parallel, right? Does that make sense? So the slopes would be the same, okay? All right. How would I draw this picture? Let's say I'm gonna start up here, moving pretty fast in the negative direction, and I'm gonna slow down. So start the stopwatch, stop the stopwatch. What's that gonna be? What's that gonna be?
You start from a distance of like 5, right?
Okay, so I'm starting, good, so I'm starting with some positive initial value, right? So I'm starting up here somewhere. Okay, now here's the part, now let's get the shape of this thing. So I'm starting up here, okay, fast, slowing down, 0.
Steep slope to west.
Ah, okay, so steep slope, now what's the slope gonna be? So if we take a snapshot of my initial, what I'm doing initially, I'm cruising along in which direction? Negative. So I'm going fast in a negative direction. What is that?
So steep down.
Okay, so that's a big negative velocity, so the slope should be very negative, right? So something kind of like this. There's maybe the tangent. Further along though, I'm slowing down in the negative direction, so my tangent line should start to maybe look a little bit more like that, right? And by the end, what should it be? Should be flat, okay? Right? Does that make sense then, that it's gonna look like that? Everybody see that? That tells the picture, doesn't it? That tells the story. I'm moving fast in the negative direction while decelerating to rest at 0, right? Okay, how about if I do this one? This is gonna be really tricky. Let's say I'm going fast in this direction to start with. So start, slow down, pick up speed in the negative direction. What's that gonna look like? Now think about that for a second. Scratch that out in your notebook, see if you can get that one done. Once again, let me remember what I did. Okay, so here we go. Ready, start. Stop.
Are you at an approximate speed the whole time?
I'm uniformly changing my speed.
Wait, are you starting out?
So once again, so I'm going, I'll do it slow motion. So cruising along, going fast, start. Now slowing down, stop, and then I'm gonna pick up speed in the negative direction, and I'm gonna come by the starting line, going fast the opposite direction.
But when you say starting,
So I'm starting right now.
you're starting at 0. Oh, you're starting at 0.
Stop. Okay, so think in terms of my initial position. What's that going to be? 0. What's my final position? 0. What's my initial velocity? No, I'm going fast in that direction to start with, right? Right? So my initial velocity is big and positive because I'm starting it now. Stop.
Oh, wait, so you're starting and stopping at 0.
Yep.
Last time you said he's going past the start line.
So wouldn't it be like one of those or is he not?
Yeah, it's
So we got 2 points for sure, right?
Yeah, 0. So it goes like.
What's he gonna do in between?
Like the.
So it's gonna
Goes up,
accelerate
and then it goes down.
and then decelerate.
Okay, so yeah, now maybe we even know one point in the middle. Because if I'm starting, what about right there?
That's
One.
your maximum.
What's my velocity right there? Interesting. So what's that mean about the tangent line?
What?
It's gotta be flat,
Which
right?
is gonna be the average velocity.
So I got a point up there, right?
Yeah.
I know the tangent line up there has to have a slope of 0 because I'm at rest right here, instantaneously, right? Everybody see that? So what's that gonna look like?
Hey, Jonathan.
So, okay, so is it gonna look like this?
No.
No, it's not, thankfully. Because that would kill me if it was like that, honestly. It would, because nothing in the real world with mass could do that, because I would be increasing. What this would be doing is I'd be going from positive speed to negative speed instantaneously, which with instantaneously, which would kill me. So thank you for not making me do
How
that.
do we know that? Why did that kill you?
Well, because how could you instantaneously go from moving in this direction at some speed to moving in that direction at some speed? Yeah, I mean, that would be,
Wow.
that'd be infinite acceleration. It's just like saying, and we'll talk more about this later, if you fall off a building, it's not the fall that kills you. Yeah, it's the end, it's the change in direction or the change in speed that kills you. So what's he gonna do? I think I heard it. Johnny?
You're gonna, like,
So, like this?
Yeah.
Almost, there's only one part of that I don't agree with. That's why it's too complicated.
Then maybe it's just like, there's like a rounded top, it just goes straight down.
Okay.
Okay.
See, this isn't quite right, because what this is saying, this is way more complicated. What this is saying is that I'm starting off from rest, and I'm picking up speed and coming to a rest, gradually picking up speed and slowing down at the end. Because look, see, my tangent lines are getting flat at the end. Shouldn't do that. Instead, isn't ours just gonna look like this? Isn't ours just gonna be simpler? It's just gonna look like that. Right? Make sense? Now think about the tangents. I'm starting off with a steep positive tangent, because when we started this thing, I was moving fast in that direction, right? I'm losing speed, coming to rest right here at a certain displacement, a certain position, positive position, right? Velocity is 0, and then it's gonna get gradually more and more negative towards the end. Everybody see that? Okay, good talk. That's, we'll pick this up later, but that kind of gets you going on that first assignment, chapter 5. It's real conceptual.